In this module, we'll be looking at scope traces from the engine's pressure sensors. We'll configure them for best results and see how to identify a known good trace. The scope we'll be using today doesn't have a noise filter, but if yours does, I recommend turning it on. Pressure sensor data is invaluable when working with and diagnosing pressure-related faults. Most OEMs won't provide a scope trace for their sensors, so use this video as a reference for correctly functioning sensor outputs. Oil pressure switches range from single to multiple terminal, and in some instances can even affect the vehicle from starting if pressure isn't seen. Using a pressure gauge is great, but using a scope is much faster and can check the electrical integrity of that circuit. Connect the sample lead to the signal circuit and the black lead to ground. Set the Y-axis to 20 volts and the X to 1 second. This vehicle has a single wire oil pressure sensor, so we should see the voltage trace start at 0 volts with the ignition on, then shoot upwards of 12 volts with the vehicle running. On a multiple pin connector, back probe the signal circuit and the other to ground. Adjust the scope's Y-axis to 10 volts and the X to 2 seconds. On this vehicle, we can see the trace at key off, key on, and engine start, followed by an increase to 4,000 RPMs. The fuel rail pressure sensor is another component that provides pressure information to the ECM for finer adjustments to fuel delivery and emission control. To connect, back probe the sample lead at the signal circuit, then adjust the Y-axis to 10 volts and the X to 1 second. Place the black lead on a known ground. At idle, we should see a constant voltage, but during a road test, the trace should rise with an increase in acceleration and load. We may need a second tech to perform this safely. Under hard acceleration, we should see the trace spike, then slowly drop as the RPM is reduced. On this particular vehicle, we can see when the AC cycles, as well as gear changes. The map sensor lives in the manifold or on the firewall. Its role is to transmit manifold pressure data to the ECM. To connect, back probe the sample lead at the signal circuit and attach the black to a known ground. Set up the scope with a Y-axis of 10 volts and a time base of 1 second. With the key on and engine off, the pressure value will be atmospheric. This is indicated by a constant voltage display. Start the vehicle while watching the trace. The reading will change as the manifold is now under vacuum. Like the fuel rail pressure sensor, it might be necessary to road test the vehicle under different operating conditions. This trace shows the vehicle accelerating. It should be repeated several times so we can collect as much data as possible. This trace shows the vehicle under load going uphill. The airflow meter is not a pressure sensor, but is a device that measures the amount of air entering the engine. So, while we're in the area, let's scope this too. To connect, back probe the sample lead to the signal circuit of the airflow meter and the black lead attached to a known ground. Set the Y-axis to 10 volts and the X to 1 second for the best display. Start the engine and examine the trace. At idle, a correctly functioning trace should look like this. There is a constant voltage reading with no major changes. Capturing a trace while performing a road test may show faults under different load and engine speeds. This is what a good mass airflow sensor trace looks like under hard acceleration. We can see the voltage rise and fall according to the driving conditions. The AC pressure switch is used to relay the pressure within the system to the ECM for safe compressor operation. Back probe the sample lead at the signal circuit and the black lead attached to ground. Adjust the Y-axis to 10 volts and the X to 1 second. For this vehicle, on a 22-degree day with the air conditioner switched off, our trace looks like this. Be aware that the pressure values will change based on the ambient temperature. This will affect the voltage signal. With the engine running at idle and the air conditioner switched on, the trace voltage will rise slightly. An increase in RPM will have the same effect. As soon as we accelerate to wide open throttle, the compressor cuts out. This can be seen as the trace drops at just under 2 volts. The knock sensor is a vital component for pre-detonation detection and prevention. Again, this isn't a pressure sensor, but is similar in operation. The knock sensor uses a piezo element that converts vibrational information into an electrical signal. Backprobe the sample lead at the sensor signal circuit and attach the other lead to ground. Set the y-axis to 2 volts and the x to 5 milliseconds. This is what a correctly operating NOx sensor trace looks like at idle. Let's take this vehicle for a road test and watch the trace under different load conditions. Under cruise throttle, we can see the trace is very similar to what was observed at idle. However, under deceleration, the trace oscillations are reduced. This is normal, as there are no combustion events due to injector cut under these conditions. Now let's put the vehicle under high load driving conditions. We can see that the trace oscillations have increased in amplitude and time due to these extreme combustion events. For more information on NOx sensors, please watch our other training modules on piezo devices. The boost pressure sensor measures the turbocharger's boost pressure. To connect to this sensor, backprobe the sample lead to the signal circuit and the black to chassis ground. Adjust the y-axis to 10 volts and the x to 1 second for the best trace display. This is what a correctly working sensor looks like. At idle, the trace sits at a constant 2 volts. When driving under normal conditions, the higher charge air pressure causes the trace to rise. The low pressure fuel sensor is located just after the fuel pump. It communicates with either the ECM or the fuel pump control module. Backprobe the sample lead at the signal circuit and the other to chassis ground. Adjust the y-axis to 10 volts and the x to 1 second. With the vehicle off, we can see the voltage is high. On engine start, the trace drops slightly. When we increase the engine speed from 2000 to 4000 RPMs, there is no change in the trace. This confirms a constant fuel pressure. Half the battle when scoping any component is knowing what a good trace should look like, followed by using the best time and voltage scales. As the old adage goes, practice makes perfect. So keep at it and cement your skills as a modern day tech. Thanks for watching. See you soon.